Okay, so let's do number one. This is on the mid-chapter review. So it tells us a large merry-go-round has a radius of 2.3 meters. Sally's sitting 0.8 meters from the center, and Frank is going to push the merry-go-round at the outside edge from rest and let go of it after one rotation. And at that point, he's running at 1.8 meters a second. And then the questions ask us about Sally's tangential and centripetal acceleration. All right, so here's the deal. So we've got this merry-go-round, right? Sally is sitting kind of here, partway out, and Frank is at the outside edge pushing on the merry-go-round, all right? So what's at the crux of this is because Frank and Sally are kind of moving with the merry-go-round, they're going to share the same angular values, right? In other words, in the time it takes for Frank to run one rotation around the merry-go-round, Sally's also going to complete one rotation around the merry-go-round. So all of their angular values are the same. All right, so number one, here's the crux. All right, the angular values are all the same for Frank and Sally. All right, so the idea is if I can find, for example, Frank's angular acceleration, then I also know Sally's angular acceleration. Okay? So that's the deal. All right, now, before I go on, I'm going to use F for Frank and S for Sally. This is why I don't usually use Frank in my problems. F also stands for final. So I'm going to use capital F's for Frank and lowercase f's for final. Capital F Frank, lowercase, so final Frank. Okay? Okay, so let's write down all the stuff we know. So first of all, the problem gives us a whole bunch of information about Frank. So here are the things that we know. We know that the circle that he is running around in has a radius of 2.3 meters. I know that he begins at rest, so his initial velocity is 0. His angular initial velocity is also 0, right, because he's not moving. I know he's going to go one rotation. So remember, one rotation is a measure of change in angular position. Okay, so that's one rotation, multiply by 2 pi and find out that that's 2 pi radians. Okay, and it tells us that at the end of that one rotation, he's got a final velocity of 1.8 meters a second. Okay, and what we want to know is, the question wants to know, over here for Sally, we know her radius is 0.80 meters. We know that she begins at rest. She's also going to go through one rotation, right? So 2 pi radians. Remember, they have the same angular values. And what we're trying to find in part A is we're trying to find her tangential or linear acceleration. Okay? So somehow I need to use this information about Frank to find out something about Sally. Okay? And so the idea is this. If I can find Sally's angular acceleration, then I can use a jumper to find her linear acceleration. Okay? So again, here's the deal. Well, Sally's angular acceleration is the same as Frank's angular acceleration. So if I can find Frank's angular acceleration, then we've done most of the hard work. Okay? So, most of the values I've got here are angular, and I'm looking for an angular quantity. So this is the guy that's jumping out at me and looks like it's causing some problems for us. Let's use a jumper and convert that, okay? So let's find Frank's final angular velocity, all right? So I guess I'm using green to represent Frank here. So this is going to be, what, VF over R, right? Angular is linear over radius. So I'm looking at 1.8 meters a second divided by his radius of 2.3 meters. So divide that excuse me, out, and it gives you a number that I wasn't smart enough to write down. 1.8 divided by 2.3, so it gives you 0.783 radians per second. Okay? So now look at all the angular information I know about Frank. I know his final angular velocity, I know his initial angular velocity, and I know his delta theta. So I think that I ought to be able to do this guy. 2 alpha delta theta equals omega f squared minus omega I squared to find alpha for Frank, right? Okay, so plugging in those numbers that I highlighted there in yellow and solving for alpha, we discovered that Frank's angular acceleration is 0.0487 radians per second squared. Aha! Well, that means then that Sally's angular acceleration is the same. Okay? So, angular acceleration for Sally is that same number. So now I can find her regular acceleration by using another jumper. So let's see, her angular acceleration is 0487 radians per second. Her radius is 0.8 meters. So multiply that and it gives you 0.039. Oh shoot, I got my units wrong, don't I? Sorry. Squared, meters per second squared. And there's your answer for that. Okay? Yeah, okay. All right. So that's part A. Part B wants to know her centripetal acceleration. So to do part B, let's do that in red. Centripetal acceleration is v squared over r. So I know Sally's radius, I got to find her velocity. So let's see. So a minute ago, we calculated that Frank's final angular velocity was, what was that number again? 0.783 radians per second, right? Oh, well that means that Sally's final angular velocity is also 0.783 radians per second. And so I can use a jumper. V equals omega r, 0.783 radians per second times the radius of 0.8 meters. And that gives us a number that I also didn't write down. This is 0.626 meters per second. And now I can find her acceleration. Acceleration is v squared over r. So just take the 6.626 meters a second, square it, divide it by her radius, and that gives you 0.49 meters per second squared. All right, so there you go. That's how you do number one.